Hello students, welcome to my YouTube channel. This is the 37th lecture in linear algebra, and in this video lecture I will be discussing linear transformation and matrices. Again, one of the very important topic from examination as well as competitive point of view. So let's discuss what is the relation between a linear transformation and a matrices. Let me clear that every linear transformation corresponds to a matrix, right? For this, let T be a linear transformation which is defined from V to W, right? So this is a linear transformation, and let us consider a field to be F, right, over the field F and over the field F, right? And let me take the dimension of V to be N and the dimension of W to be M. So now let us define the basis set. So let B1 be the basis of V, that is, let B equals to V1 comma V2 and so on to Vn. So this is the ordered, so very important, ordered basis of V. Now why this word order is very important, this will be clear once we practice few questions as well as once we derive the things. And similarly, if I consider B2, that is the basis, order basis of W, so let it be W1, W2 and so on to Wm. So this is a ordered basis of W, right? So what I need to do is I need to find the metric representation of T of this transformation with respect to bases B1 and B2, right? So that is, you have to find a matrix corresponding to this transformation T, okay, with respect to basis B1 to B2. For this, I will be considering any vector V, which is any arbitrary vector that is coming from capital V. Since this is an arbitrary vector from capital V, so it can be represented in the linear combination of the elements of the basis of V. So this is alpha and Vn. Now apply T on both sides, apply T on both sides. So once we apply T on both sides, so what do we get? That is T of V equals to T of alpha 1 V1 plus alpha 2 V2 up to so on to alpha n Vn. Now since we know that T is a linear transformation, so you can apply the property of linear transformation. So this will be alpha 1 times T of V1 plus alpha 2 times T of V2 and so on to alpha n T of Vn. So why I have written this? Because by the definition of linear transformation and because it says that T of alpha V is always alpha times T of V, right, using this property. So I think this thing is clear now. So can I say what is the T of V? That is the range, right? So range of T is spanned by, so can I say it is spanned by T of V1, right, comma T of V2 and so on to T of Vn. Now, since my range of T is spanned by T of V1, T of V2 and so on to T of V1, and we already know that T is a transformation which is defined from V to W, right? So if you calculate T of V1, so this will be one of the element from W, right? Not exactly one of the element, that element can be represented in the linear combination of the basis of the elements of the basis of W. So that is what we are going to do now. So my T of V1 will be in a linear combination, that is, let me call the scalars as alpha 11 W1, right, plus alpha 21 W2 and so on to alpha M1 Wm, right? So the last vector was M. Similarly, if we calculate T of V2, so this will be again alpha 12 W1 and so on to alpha M2 Wm, right? And similarly, if we calculate T of Vn, so what it will be? It will be alpha 1 n, right, W1, and the last entry will be alpha, this is Mn Wn, correct? Now my next step will be, I will be writing, and let me mention here that all my alpha ij's, they are coming from the field, right, F. So now the coefficient matrix corresponding to this system of equation. So the coefficient matrix corresponding is, see, alpha 1 1, fine, next is alpha 2 1 and so on to alpha M1, correct? Similarly alpha 1 2 and so on to, this will be alpha M2, correct? And the last will be alpha 1 n up to alpha Mn, right? So this is my coefficient matrix. So now if we take the transpose of this matrix, so we get a matrix representation of a T with respect to basis B1 to B2. So now I can write it as T matrix T from the basis B1 to B2, and that will be equal to the transpose of the coefficient matrix. And once you take the transpose, it will be alpha 1 1, alpha 2 1, and so on to alpha m1. Similarly alpha 1 2, right, and so on to alpha 1 n up to last it will be alpha m n, right. So this is again an m cross n matrix. So this is a metric representation of a T with respect to basis B1 and B2. Now let us solve few examples to understand this concept. So the first example is, so let T be a linear transformation which is defined from r cube to r square, right, and my map is T of x y z is equals to x plus y comma y minus z, right, and B1 is given to us as 1 0 0, so standard basis 0 1 0 and 0 0 1, right, and B2 is again standard basis of r square, that is 1 0 and 0 1. So these are the bases corresponding to r cube and r square respectively. So our first work will be, we need to calculate what will be T of 1 0 0, then T of 0 1 0, and again T of 0 0 1. Easily you can see T of 1 0 0, just apply the definition. What is T of x y z? So this is nothing but x plus y comma y minus z, right. So if it is 1 0 0, in that case this will come out to be 1 0, correct. And next T of 0 1 0, so again this will be 1 comma 1, and if you calculate T of 0 0 1, so just substitute z equals to 1 and rest of this to be 0, so this will be 0 comma minus 1. Students, you can easily see that I am using the same strategy which I have explained above, right. So we are finding T of v1 and so on, right, and now I will be writing it in the linear combination, right, in the linear combination of the elements of the basis of r square, right. So the next job is to find constants, right. So some constant times 1 0, right, plus constant times 0 1. So why they have mentioned ordered basis? Because you have to use this order only, right. Here it should be 1 0, here it should be 0 1, right. So that is the importance of ordered basis. Similarly you need to write this as alpha times some 1 0 plus some another constant times 0 1, and similarly for the last one. So now our task is to find these coefficients. How can we calculate these coefficients? From here it is very easy, you can easily observe from here. So 1 0 can be written as 1 times this and 0 times this, correct. How can you write 1 1? So 1 times this plus 1 times this, and you can easily verify, right. Here it should be what, 0 times this vector and minus 1 times this vector. And what is the next step? We find the coefficient matrix as I have explained above. So the coefficient matrix will be 1 0 1 1 and 0 minus 1, and the next step, that is the last step, that is you need to find the transpose of this matrix, right. So that will come out to be 1 1 0. So next will be 0 1 and minus 1, and that is the answer. The second question is, T is a linear transformation which is defined from r square to r square, which is defined as T of xy equals to x plus y comma x minus 2y, and the bases corresponding to r square are 1 2 and 2 1 for this particular question. And again we have to find the matrix representation. So let us solve this. So the same strategy, so we'll be calculating T of 1 2, so this will be 1 plus 2 1 minus 2 to the 4, right. So this is nothing but 3 comma minus 3, correct. Now calculate T of 2 1, so this will be 2 plus 1 comma 2 minus 2 into 1, correct. So this will be 3 comma 0. Now what is our next task? Next task is to write 3 comma minus 3 and 3 comma 0 as a linear combination, alpha times 1 2, right, plus beta times 2 1. Similarly alpha times, so let me call it that alpha 1, so alpha 2 times this is 1 2 plus beta 2 times this is 2 1, correct. Now you can easily find these through hit and trial even. So let us see how can we find it by hit and trial. So guys, again it is very easy also, but you can even find the system of linear equations and you can calculate. So first if we find alpha 1 and beta 1 from here, so this will be alpha 1 plus 2 beta 1 is equals to 3, and 2 alpha 1 plus beta 1 is equals to minus 3, correct. So and the system corresponding to this, it will be alpha 2 plus 2 beta 2, right, is equals to 3, and 2 alpha 2 plus beta 2 is equals to 0. Now we need to find alpha i's and beta i's, right? So you can easily solve this. You can just multiply this by 2. So you'll be getting 2 alpha 1 plus 4 beta 1, this is 6, and 2 alpha 1 plus beta 1 is equals to minus 3. So just subtract these equations, and what you will getting is 3 beta 1 is equals to 9. So beta 1 comes out to be 3. So if beta 1 is 3, so you can easily calculate alpha 1. Alpha 1 will be 3 minus 2 beta 1. So that is 3 minus 2 into this is 3. So that is minus 3. So I have represented my alpha 1 is minus 3 and beta 1 is 3. So I can write it down. So this is minus 3 and this is my 3. Correct. Now next task is to find alpha 2 and beta 2. So again it's a easy task. You can just multiply these equations. So 2 alpha 2 plus 4 beta 2 is equals to 6, right? And 2 alpha 2 plus beta 2 is equals to 0. So just subtract these equations. So what you get here is 3 beta 2 is equals to 6. So beta 2 comes out to be 2, right? And similarly you can find out the value of alpha. So what will be my alpha 2? That is minus beta 2 by 2. So that is nothing but minus 1, correct? So this is nothing but, so my alpha 2 is minus 1. So let me write it here, minus 1. And what is my beta 2? That is a 2. So we have calculated the values of alpha i's and beta j's. Now we just need to form the matrix, and as I've already described, so let me take the coefficient matrix. So students, I'm writing it here. So this will be minus 3, 3, minus 1 and 2, and the last step is just take the transpose of this matrix. So this will be minus 3, 3 and minus 1 and 2. So this is the metric representation of this linear transformation with respect to a given basis. So in this question I have tried to explain that if my bases are not standard, then how can we calculate the matrix representation corresponding to those bases. So I hope these two questions are clear and the strategy is clear in this video lecture. In my upcoming video lecture I will be discussing few more questions which have appeared in IIT JAM or CSIR and UGC NET from this particular topic. So I hope you have enjoyed this session. Thanks for watching my video. For more such videos, do subscribe to my YouTube channel and share these videos among your friends. Thank you so much. Thank you.